good morning, everybody. So we've heard talks now about how planets form and about the structure of protoplanetary disks. And what I would like to do is to conclude this sort of context setting by telling you about the physical and chemical processes in the regions where new stars are forming. And so since not all of you may have an astronomy background, I would like to actually start with a little bit of introduction. So this is what the sky in winter would look like if you look up from, for example, Vilnius. I think April is a little bit late, but next year you have a chance again. So you have here the constellations of Orion and Taurus. And if you look closely, maybe not from downtown so much, you can actually see that there is more than just stars in the sky. You have, at this point in Orion, a nebula, which, if you blow it up with a space telescope or so, looks like this. It's a large cloud of gas where indeed new stars are forming. But you also have other nebulosities, so you have to be careful. For example, this here is actually, when you look carefully, it's a cluster of young stars. You can tell that they're young because they're still surrounded by a little bit of gas. And it's been known since a long time, for example, in this Bronze Age Nebula disk. And there are even different kinds of nebulosities, like this one in the constellation of Orion, and that's just a large collection of stars. This is what our Milky Way would look like if you saw it from the outside. And so this is a totally different scale, right? So we're talking here maybe hundreds of light years in size and distance, and this is more like millions of light years away, and also much, and maybe thousands of light years across. What we have learned in the past couple decades is that stars don't live forever, right? But that they're rather part of a cycle of gas in galaxies. So we are here, right? Our sun, in a few billion years, will swell up and expel most, maybe half or so of its mass, back into the so-called interstellar medium. And so all the gas together of such old evolved stars gathers again in clouds. And there are two essential kinds of interstellar gas clouds. So you have diffuse clouds, where most of the gas is in atomic form, and these clouds tend to be transparent for UV radiation, so that warms them up to perhaps 100 K or so. And then these clouds slowly contract and thereby cool until you get so-called dense clouds, and there most of the gas is in molecular form, and they are dark and opaque to UV radiation, and that was their main heating source, so they'll be cold, more like 10 or 20 K. And it's in this kind of cloud where new stars are forming. Overall in this cycle, what we really like to understand, and also is very much the topic of this conference, of course, is how volatiles, in particular water and organics, are delivered to planets, and how much of this volatile reservoir is indeed interstellar. So keep that in mind during this talk. So to study these dark clouds where new stars are forming, we clearly can't use optical or infrared radiation, because we won't see anything, they're too cold to emit, and also the dust just hides our view on these clouds. So we need to go to long wavelength, and in particular the far infrared is really good. Here's an example taken with the Herschel Space Telescope. So as André already mentioned, the bulk of these clouds is in the form of molecular hydrogen, but we can't see that at low temperatures. So we need to use tracers, such as dust continuum, that's what we're seeing here. You could also use other things like CO lines. Dust is better because it has higher dynamic range. And so what we actually see are these sort of elongated structures, people call them filaments, which sometimes also have these so-called dense cores, these density enhancements, right? And you have two basic kinds of dense cores, and they're color-coded here, blue and green. And these are respectively with or without a near-infrared source. And what does it mean when a core has a near-infrared source? Well, it must mean that it has internal heating by a young star that is forming, right? And so you distinguish, so these with a heating source are called protostellar cores, and if they don't have a young star yet, we call them pre-stellar cores. And so these cores are dense enough that they can actually collapse under their own gravity. Now you may ask, of course, so how did we get these filaments and these cores? And one thing we can also do in the far infrared is study the polarization of the dust continuum emission. And here's an example from the Planck satellite. So here's another filament that you see again. And these little arrows here are the direction of the magnetic field inferred from the polarization measurements. And what you can see is that the filament is actually more or less perpendicular to the magnetic field direction. So what we think is that these filaments form by magnetic channeling of wind motions. And so where you get these filaments where winds are colliding, for example. So it's in the beginning of the cloud formation stage, you have these turbulent flows which are channeled by magnetic fields. And then later, when you get to the dense core stage, gravity takes over and they collapse to form stars. Good, so let's now look at what actually conditions are like in these prestellar and protostellar cores. So here's a prestellar core, and this is just for illustration. Yeah, that's why you can't use optical light, because you don't see anything. Although it looks pretty, it's good for PR, but not so much for science. Much more useful is this kind of image in the far infrared, or even in the submillimeter. This is taken from the ground. Where you can see that it has a pretty simple structure, almost round and very much centrally condensed. So you can infer the densities and also temperatures from the continuum and line irradiation in the far infrared. Good. And then when you get to the protostellar stage, things become a bit more complicated. It's sort of sketched here. So the remnant of the core is now called the infolding envelope. So you have these infolding motions, but stuff doesn't fall directly onto the star, but it first falls onto this disk. We heard already about what happens then in these disks. And then from the disk, material accretes onto the star, but also a fair fraction is actually ejected in bipolar outflows. Yeah, that has to do with angular momentum conservation. And conditions in these kinds of cores. So in the prestellar cores, things are really cold, just between 5 and 10 K or so. And densities are, well, what to interstellar standards, this is high, obviously much, much lower than in this lecture room, for example. Then when you get to this protostellar stage, of course, the central star helps heating up stuff. So you get a larger range of temperatures, perhaps to a few hundred K or so. The densities are like in the prestellar core. In these outflows, temperatures actually get a lot higher because it's also shock heated, right? Densities tend to be lower. And in the disk, well, we just heard about the disk, so they have also a large range of temperatures and densities. Densities tend to be actually quite high. And as I mentioned, so the difference between these prestellar and protostellar cores is that the prestellar cores are only externally heated, right, by interstellar UV radiation and also by cosmic rays. So these are energetic, like MEV kind of energy particles that travel around the galaxy and help heating clouds and also ionizing them. And then in the protostellar case, you also have internal UV and X-rays from the central star and the star-disk interaction region. Good. So this is about the formation, all about the formation of stars like the Sun, and that's the main kind of star. Most stars are more or less like the Sun, a little bit bigger, a little bit smaller. But you also have a rare type of star known as the high mass stars, like 10 times the mass of the Sun or so. And these are rare, but they're very important for the evolution of the galaxy as a whole. Because they're much more luminous than the Sun and also have hotter surfaces. So they're actually the main source of ionizing and dissociating radiation, UV in particular, in the galaxy as a whole. And also their interiors are very important because they are the main source of heavy elements, which we also need, of course, to start life. So they're the main sources of like carbon and upwards towards iron, and in fact they're the only source for elements heavier than iron. And they're so important for the evolution of the galaxy because they're also active mechanically. They blow very strong stellar winds, and that leads to big bubbles in the galaxy that then are filled by hot ionized gas, and you can see them in X-ray pictures like these. This is the Eridanus bubble. And at the end of their lives, they don't just swell up but they in fact explode as supernovae. This is the Crab Nebula, the remnant of the supernova that went off and was seen from China in 1554, right? And these supernovae are important, for one thing, to create heavy elements, but also to create these cosmic rays that are important to heat up our clouds. And so these are very important to understand the ecology of the galaxy. But it's also important to understand the formation of high mass stars because, in fact, for distant galaxies, all we can see are the massive stars. So to understand at all how the first galaxies formed and so on, we have to have a good understanding of massive star formation, and we don't have that. Okay. So that was the first part, and now in the second part of this talk, I would actually like to go into the chemistry of these star-forming regions more. I'll go over these different kinds of cores in a sec, but I'd like to make a few basic points about interstellar chemistry. The first thing is about elements. So forget the periodic system. Here is what things look like in interstellar space. Almost everything is hydrogen. There's some helium, and there's just little bits of other things, mainly carbon, nitrogen, oxygen, and then if you look really carefully, you can find other bit heavier elements. And everything else is at unimportantly low levels. And why is that? Well, basically the fact that we have mostly hydrogen and helium tells us that our universe is young. There hasn't been enough time for stars to produce the other elements in large amounts. So they do their best, of course, and so the main stellar products are carbon, nitrogen, and oxygen. So that's at the 10⁻⁴ level, but we're far from an equilibrium state, essentially. Okay. The second key point about interstellar chemistry are these low densities. Yeah, much by orders of magnitude lower than, for example, in this lecture room, and that has two important consequences. First of all, we only need to care about two-body reactions, right? Unlike here, where you have three-body reactions occurring, we don't have that in interstellar space. And the other thing is that chemistry is usually limited by the kinetics, not by thermodynamics. So this has the consequence that the chemistry is often time-dependent, which is useful. We can use it to learn about the ages of certain objects by modeling their chemistry. All right, and then the third and final key point is that dust grains play a large role, as we already heard in the previous talks. In fact, they play a double role. So here's a mid-infrared spectrum of some star. And what you see are these absorptions by solid-state species. So they're broad absorptions. Here's water ice. Here's carbon monoxide ice. So these are molecules that are freezing out onto the surfaces of dust grains. And we observe these mid-infrared vibrations in absorption. And we can also see that the dust grains are actually playing an active role, not just reservoirs, but also factories. Because we see the products of hydrogen and oxygen addition reactions. Oxygen addition makes carbon dioxide, and hydrogen addition to CO makes methanol, as seen in this absorption. So the dust grains play a very important role in the chemistry. Good, so let's now look at specific kinds of objects and see how their chemistry varies. So in this first pre-stellar phase, things are relatively simple. Densities are high, temperatures are low, so what does that mean? We have a lot of depletion of molecules onto dust grains. And you can see that in images like these. This is the same pre-stellar core as before. And what you can see in the CO image is that there's actually a hole here at the center. So CO is not seen in the gas phase, it is frozen out. The N2H+, by the way, is not yet freezing out. So there's a whole sequence, right, of depending on how volatile a species is. So the water freezes out easily, ammonia and methane take longer, CO takes even lower temperatures to freeze out, etc. And in principle, if you carry this all the way through, you would end up in a complete depletion limit where only hydrogen and helium would remain in the gas phase. So maybe this occurs, it's possible. One consequence for the gas phase is also that it has a strong effect on deuterium to hydrogen ratios, which is also of interest for the origin of water on Earth, as we heard, for example, yesterday at the planetarium. Normally the reservoir of deuterium is Hd, but at low temperatures it gets transferred to H2D+, and this is actually a quite active, chemically active species. It can transfer its deuterons to other species, and for example, here was one of the first detections of fully deuterated ammonia in interstellar space. Triply deuterated is still the world record in terms of deuteration. And since the cosmic deuterium abundance is only 10⁻⁵, if you manage to get 3 substitutions, it is effectively an enhancement over normal state of affairs by 10 to the 15. So this is very large deuterium enhancements indeed. Good. So, but things don't stay forever in the pre-stellar phase. New star forms. What does it do? It heats up its surroundings. And we see that in spectra like these of so-called hot cores. So they have a quite rich organic content. So you get species like dimethyl ether, and here's ethyl cyanide, etc., etc. And conferences are where it's good to bridge cultural gaps. And one gap that should be closed is that astronomers tend to think of these things as complex organic molecules. And I'm sure to the organic chemists in the room this must be a bit of a laugh, because they are used to thinking about proteins and whatnot, which are, well, quite a bit more complex than these. To them, this is still simple species. And we actually, there's actually been some evolution in the thinking about how these species are formed. So classical theories have them form, just have ices evaporate and do gas phase chemistry, what does the rest of the work, combines, for example, two alcohols, two methanols into dimethyl ether. But more recent models actually have a lot of things happening in the ice layer when it is still warming up, but before its actual evaporation. So, so this is a field of current study, I would say. Also, we don't actually know quite where all this organic emission is coming from. So here's a recent ALMA result by a student in Groningen, Veronica Allen, of a disk which actually you see this spatial segregation. Different molecules have these different spatial distribution, and we don't quite understand what that means. We're working, for example, with Catherine Walsh in Leiden to understand this better, to understand whether this is an inner envelope, is it a disk, or is it an outflow cavity. Okay, so a quite different kind of environment is provided by these bipolar outflows that I mentioned that are emanating from protostellar systems. Here's an infrared picture of shocked molecular hydrogen. So this is gas heated to perhaps 1000 K or so, but by shocks. So that's one thing that these outflows do. So the typical velocities are like 10 to 100 kilometers per second. And if this slams into the surroundings, it creates a strong shock. And this so it heats the gas to maybe 1000 K or so, and this atomizes basically the gas, and it also shatters the grains, both the mantles and the cores. And this leads to strong enhancements of abundances of certain species. So here's a millimeter wave observation of so here's the protostar, and here are the outflow lobes, and you see that the emission is very strong in, for example, SiO and methanol. So these are typical results of what happens if you shock interstellar grains. Yeah, you get these products of the grains. And the other thing that outflows do is they create cavities, right? So here's a similar picture of what I showed before at the anatomy. So here's our central star. Here's the infalling envelope again, and this outflow creates this low density cavity, and that creates an opportunity for stellar UV radiation to actually irradiate these cavities, warm them up, and also damage the molecules, really. So what you get is this strong emission in hydride molecules. Yeah, so these are products of UV dissociation of more complicated molecules. And in fact, this happens also on a larger scale, these radiative feedback of young stars onto their environment. So star formation doesn't just create more complicated molecules, it also at the same time does a fair bit of destruction. So here's a region in the Orion molecular cloud. So there are hot stars up here, and they irradiate this molecular cloud, which is sitting here, and it leads to this stratified structure, both in terms of the temperature and also in terms of the composition. And you get this strong emission from ions and radicals. Here's, for example, CH plus emission, quite broad, and here's also C plus, which is dissociated CO, essentially. So in this kind of region, they're known as photon-dominated regions, and so the chemistry is really driven by photoprocesses, in particular photodesorption and photodissociation. Good. That is what basically my overview of interstellar chemistry. Let's just summarize. I hope I have convinced you that astrochemistry is great by itself, but also as a tool to understand physical conditions in space, and also to understand chemistry. And people think of interstellar chemistry of exotic, but that is of course turning things upside down. It is our Earth which is exotic, and interstellar space is the natural state of affairs. All right, and otherwise we have a wide range of physical and chemical conditions, right? In pre-stellar cores we have cold and dense conditions, and that leads to strong depletion of molecular species onto dust grains and enhanced deuterium-hydrogen ratios. And probably on the surfaces of the dust grains, you have these hydrogen and oxygen addition reactions occurring. And then after a protostar form, you have evaporation processes, but also shocks and UV. So there's quite a lot of feedback from the protostar, and this leads to rich organic spectra, so that's good. But it also leads to shattered grain cores and mantles, and to all these radicals and hydrides as a result of ultraviolet emission. So what does that mean for the organics? Well, it means that they can develop and evaporate in these cores, but there are also many places where they subsequently will be destroyed. But probably the disks is their safest place where they may be able to survive and in fact reach planets like our own. So where do we go then from here? Well, astronomers are always fighting with that their objects of study are very far away. So we need always sharper telescopes. For example, the Hubble Space Telescope is at the distance of the nearest star-forming regions, limited to spatial scales of maybe 10 AU or so. And we would like to do better, so the ALMA telescope, which Anne already mentioned, is doing that for us by a factor of a few. Still, this isn't good, so the bigger and better telescopes will continue to be important, in particular to understand the formation of high-mass stars, and also, of course, variations of star formation across galaxies. That is a topic that I haven't really addressed, but it's also an active field of study. Infrared spectroscopy, we need very sensitive infrared spectroscopy to understand this molecular complexity and see how that develops, and I think after the coffee break we have in fact to talk about that. The importance of gas phase versus grain surface processes, and then the origin of prebiotic species. And finally, and also tied to this conference, the future has a lot of steps in petto towards astrobiology, where one thing that people are trying very hard is to see if we can find amino acids in space, if we can find habitable planets, and of course if we can find biomarkers in exoplanetary atmospheres. And that's where I'd like to conclude. Thank you very much.